In this video, we'll be going over integration by substitution. Now, suppose we have a composite function, capital F of g of x, and the derivative of capital F is equal to f, lowercase f. And so what we want to say is capital F is an antiderivative of lowercase f. So let's take the derivative of this. So d over dx of capital F of g of x. And this is a composition of functions. So what we do is we apply the chain rule. We take the derivative of the outside function, keep the inside function the same, and then we multiply that by the derivative of the inside function. Now, since we said f prime is equal to f, I can substitute in lowercase f here times g prime of x. Okay, so what this all says is that if we have the integral of lowercase f of g of x times g prime of x dx, that is going to be equal to capital F of g of x plus c. So this will make more sense as usual when we look at a few examples. But first, kind of the main thing or the key thing here is that using this sort of substitution, we can think of this as undoing the chain rule. Right, so when we are integrating a function, one way of thinking of that is undoing a derivative. So what if that derivative that we've applied applies the chain rule, or we have applied the chain rule? So doing this sort of substitution is undoing the chain rule. Okay, so all the examples that we're going to do in this video are indefinite integrals, so we don't have limits of integration. But they're all going to use this technique, substitution. So what we want to do is we want to think, is there a function in here that if we take its derivative, we get the other function that's inside the integral? So what we can see is that if we take the derivative of x squared minus 3, the derivative of that is 2x, which is right here. So this is the substitution we want to make. So what we use, or we typically use the letter u for the function that is like the inside function. So the inside function here is x squared minus 3. And if we take the derivative of that, we get 2x, and then I need to write the differential dx. So what we see is that, let me write this so these things are color-coded. Okay, so we said u is equal to x squared minus 3. And then du, when we take the derivative of that first equation, we get dx times or 2x times dx. So what we see is that this right here we're going to replace with u. So we'll say u, and then that's still getting raised to the third power. And then 2x dx is going to get replaced with du here. Okay, so now that we've made this substitution, this function is going to be a lot simpler to integrate because we just have u cubed, and so we can apply the power rule. So this will end up being u to the fourth divided by 4 plus c. Again, we need c because this is an indefinite integral. And then lastly, we're going to resubstitute in whatever we had for u. So this will be x squared minus 3 all raised to the fourth power divided by 4 plus c. And there is our answer. So what we can do here is we can actually check this just by taking the derivative of what we have as our answer. So dx of x squared minus 3 raised to the fourth power divided by 4 plus c. Okay, so I'm going to use the chain rule here. So this 4 in the exponent becomes the coefficient, x squared minus 3. The exponent decreases by 1. I'm still dividing by 4, and then the derivative of a constant is 0. So these 4's cancel, and what we see is, I didn't apply the chain rule. I took this 4 down in front, but then I didn't take the derivative of the inside part. So the inside part is 2x. And then taking the derivative of c is just 0 here. So what we end up with is 2x times x squared minus 3 to the third power, and that is exactly what we have in our original integral. All right, a second example here. We're going to use substitution again, and the reason we're going to use substitution is one way to think of these problems is if we have a function that looks like it's an inside function, so this function is, whatever, we have something getting raised to the fourth, and then we have an outside function. It's kind of like we have two different functions here. Let me write that in a different color. Okay, so the inside function we'll set as u, 3x squared plus 4. And then if I take the derivative of that equation, both sides of that equation, I get the derivative of u is du. On the right-hand side, I'm going to have 6x dx. Okay, so 6x dx is all of this, and then u is going to get raised to the fourth power. So what we'll have is u to the fourth du here. Okay, so something you want to make sure when we're doing these substitutions is that wherever we have a variable in the original integral, we want to make sure that all of those variables are getting rewritten in terms of whatever variable we're using for the substitution. So originally everything is in terms of x, so we have x and dx in the original integral. We don't want to have any of those x's anymore, so we're using u for our substituting variable. We want to make sure our new integral only has u in it. All right, so to integrate this, this looks quite similar to the last one. This is just going to be u to the fifth divided by 5 plus c, and then we need to substitute back in whatever we had for u. So this will be 3x squared plus 4 raised to the fifth power divided by 5 plus c. And again, we could check this, and this time make sure you actually apply the chain rule. So we want to take the derivative of 3x squared plus 4 raised to the fifth power divided by 5 plus c. We end up with 5 times 3x squared plus 4 raised to the fourth divided by 5 times the derivative of the inside function. That's going to be 6x. And then the derivative of c is just 0. These 5's are going to cancel. We end up with 3x squared plus 4 raised to the fourth power times 6x. And that is what we started out with. So those first few examples had substitutions that were pretty straightforward. It was basically a one-to-one substitution. Everything we had for u and du substituted exactly. These next few we don't have quite as easy of a situation. Here I'm going to set u equal to 1 minus 4 x squared, and then when I take the derivative of both sides of that equation, I'm going to have du is equal to negative 8x dx. So when we're doing this substitution, again, we want to make sure all of the x's and dx convert to y and to u and du. So we have 1 minus 4x squared is what we have down here. And then we have left over is an x and a dx, but in this equation for du, we don't have just x dx, we have an extra negative 8. So what we do is we divide both sides of this equation by negative 8. So on the left-hand side, I'm going to write this as negative 1/8 du. And on the right-hand side, we're left with x dx. So what we do is for this x dx, we substitute in negative 1/8 du. So what we have here is the integral of, I have a fraction. I could write this as negative 1/8 du in the numerator if we wanted. And then in the denominator we have the square root of u. So what we do is I'm going to pull this out of the integral, negative 1/8. So this is negative 1/8 the integral of, I'm going to write 1 over the square root of u du like this. And then I'm going to write that the radical with exponent notation. So instead of 1 over the square root of u, that would be 1 over u to the 1/2, or this will just be u to the negative 1/2 du. Okay, so we did all this kind of intermediate simplification. Now let's actually find the antiderivative of u to the negative 1/2. This will be negative 1/8 u to the negative 1/2. When we take the antiderivative of that, that'll be u to the positive 1/2 divided by 1/2, which is the same thing as multiplying by 2 over 1 or multiplying just by 2. And then plus c. It doesn't matter whether we write c inside the parentheses or outside the parentheses. C is just a constant. When I multiply negative 1/8 by a constant, that's still just some arbitrary constant. So we don't necessarily need to write the c in parentheses there. But when I multiply these two terms together, I'm going to have 2 times negative 1/8 is negative 1/4, u to the 1/2. Again, negative 1/8 times c is a constant, so I could just write that as c. It's just some arbitrary constant. Negative 1/8 times a constant is still a constant. And then lastly, we need to substitute back in whatever we had for u. So this will be negative 1/4. U is 1 minus 4x squared raised to the 1/2 plus c. And again, instead of writing raised to the 1/2, we could write this as a radical and not have the 1/2 here. Whatever floats your boat is fine for an answer. All right, in this example, we're dealing with trig functions. So we have two functions here. We have a cosine function and a sine function. And the question is, well, which one do we want to set as u? Now, when you're trying to make this decision, usually you want to set u for whichever function has an exponent. In this case, the sine function has the exponent, so we'll set u equal to sine of 3z. Okay, remember, this is the same thing as sine of 3z raised to the 10th power. So the inside function there is just sine of 3z, not sine to the 10th. Okay, now taking the derivative of our u equation, the derivative of sine is cosine of 3z, and then applying the chain rule, we have 3, and then that'll be times dz. So it looks like we have cosine of 3z dz, which is good, but we have an extra 3 in here, so we're going to divide both sides of this equation by 3, so we're going to end up with du times 1/3 is equal to cosine of 3z times dz. And now we have the substitution that we want. So we will end up with sine to the 10th of 3z, so that's going to be u to the 10th. And then we have cosine of 3z dz is going to be this part, so we're going to substitute that times 1/3 du. And we have a constant like this. It's good practice to take it out of the integral. So 1/3 the integral of u to the 10th du. So applying the power rule, we're going to have 1/3 u to the 11th over 11 plus c. So this will be u to the 11th over 33 plus c. And then we just need to make a substitution back in for u. So we end up with sine of 3z raised to the 11th, I'm going to write it right here, divided by 33 plus c. All right, and we have one last example, and this one is a technique that we haven't really seen yet. So again, my inside function here is going to be x minus 1, so we'll set u equal to x minus 1. When I take the derivative of this, I get 1 dx, so du is equal to dx. So looking at what my substitution, or what's been represented, well, I've taken care of this term with x in the denominator, and then du is equal to dx, so I can substitute for dx. The issue is I still have this x right here that I don't have a substitution for just yet. So what we do is this equation I can solve for x. If I write this as u plus 1 equal to x, I can substitute u plus 1 in for this x right here. So what we have is u plus 1 in the numerator divided by the square root of u du. Okay. What we want to do here is split this integral up into two separate integrals. So u over the square root of u plus the integral, needed du right here, plus 1 over the square root of u du like this. That first integral, well, I have u to the 2 over 2 if I want, and then I can rewrite this. Let's say I can rewrite this as u to the 1/2. So I have u to the 2 over 2 divided by u to the 1/2. That'll come out to be the integral of u to the positive 1/2 here in the numerator. Right, just subtract those exponents. And then that's du plus the integral of u to the negative 1/2 du, like this. Okay, now that we're at this stage, we can go ahead and apply the power rule. So this will be u to the 3/2 divided by 3/2, or divided by 3 multiplied by 2, plus u, negative 1/2 plus 1 is going to be 1/2, divided by 1/2 is the same as dividing by 1, multiplying by 2, plus c. So the last thing we need to do is just substitute back in what we had for u. So this will be 2x minus 1 raised to the 3/2 divided by 3 plus 2 times x minus 1 raised to the 1/2 plus c.